So here is problem 55 on page 198. This is the third of three problems in which we're finding asymptotes for rational functions. If you've looked at the two previous problems that we've worked through, we first had a rational function that had the same degree top and bottom that produced a horizontal asymptote. The second problem had a polynomial on the top of the rational function that was degree 1 more than the polynomial on its bottom. That produced an oblique asymptote. And this third case is a case where the top, in this case, is got a degree 4, the bottom has a degree 2. The difference between the top and bottom is 2 or more. And for that case, where the difference between the degree of the top and the degree of the bottom is 2 or more, the rational function will have an asymptote, but the asymptote is going to be a nonlinear function. And in this case, it's actually quite easy to see what that nonlinear function is, because all you have to do is look at the end behavior. And remember, the end behavior is just determined by the ratio of the two leading terms. X to the fourth over x squared is equal to x squared. So for large values of x, this function is going to look like x squared. And remember, what I like to do to remind you of what's going on here is I can rewrite g of x by dividing top and bottom, every term top and bottom, by x squared. When I divide x to the fourth by x squared, I get x squared. When I divide 1 by x squared, I get 1 over x squared. Down at the bottom, I'm going to get 1 minus 1 over x. And then if I ask myself, what is the limit as the absolute value of x goes to infinity of g sub x, I just have to look at the top. The top has a term that's going to infinity and a term that's going to 0. So for not very large values of x, this term very quickly becomes negligible compared to this term. The top goes to x squared. And likewise on the bottom, this term stays 1, this term gets infinitesimally small, goes to 1. And so this limit is x squared. Sort of equivalent to just looking at the two leading terms at the expense of all the other terms. All right. So what does this mean? Let's note that this particular function has got zeros in its denominator, x equals 0 and x equals 1. So not only are these points not in the domain of G, they also produce vertical asymptotes, right? So at x equals 1, there's a vertical asymptote. And at x equals 0, there's a vertical asymptote as well. But what this function is doing out in infinity is it's looking like x squared, which maybe looks like that. So we can draw this very quickly. We can note that if x is equal to 2, this is 2, 4, 8, 16, 16 minus 1. It's positive, so this function is going to do something like this. It's going to come up below here, and it's going to show up here and head back up. So that's a very quick analysis of this thing, but what you want to see is that as x gets large, indeed, the function does tend towards a particular curve, and that curve is y equals x squared. It tends toward it asymptotically. All right, and that, to close here, that's what happens when the ratio of the top to the bottom is 2 or more. All right.